Yeah, my name is Rufilo Bua. I'm a rising junior at Pomona College. And this summer I was working for the Simons Observatory, most specifically for the UCSD SAT testing team. And I was doing noise characterization. So that's what I will be talking about. So to start off with like a little bit of background for yeah. So the Simons Observatory has a telescope that is essentially designed to detect CMB. And that's a nice little picture of pretty much like showing the timescale from like the Big Bang and where inflation probably happened. And so like the light that we're detecting is the light that comes from like that early stage of the universe. So this is the picture of the telescope. It's in San Diego right now. And this is a picture of the observatory, and it will be or is at like Atacama Desert in Chile. And it's a nice little place, high altitude, and it yeah. So like it will allow for access of like 80% of the sky. So that's pretty cool. And then before I start, I have to talk about the detectors within the telescope and how they'll be working. So it's using like test bolometers, which are like a thin film superconductors operating within like its transition period. So that is pretty much what like how you would expect like the detector's resistance to change with the voltage as you also it. So at the very top there, that would be the normal period, and between that and that as it transitions to its like superconducting stage. So the data that we've been working with, we're working with data in three different states. In the superconducting state, where the voltage is around like 1 volt, and then the transitioning state, so like 3.62 volts. And then we also have data from like the normal state. So yeah. So before I start, I'll have to talk about PSD, like a power density spectrum, and what it actually means. So it essentially measures the power content of the signal against its frequency. So using Fourier analysis, any physical signal can be decomposed into like a number of discrete frequencies or like a spectrum over a certain range. And the statistical average of a certain signal as analyzed in terms of its frequency content is called like a spectrum. So the data that you'll be seeing from here is essentially in that format. Like that's what you'll be seeing. Okay, so at the very beginning, I was assigned to create like a curve fitting algorithm that we would then like continue to use to like figure out the noise within the data that we have. So if you can look at like the histogram that I have is it's a part of the power density spectra. So you can see that it kind of follows like an exponential function, and the function that we use to fit to the data is like a chi-square distribution with 2 degrees of freedom. That is the function over there, and k would be the degrees of freedom. So it like if you plug it in, you essentially just get like a simple exponential function. And yeah, so yeah. And then so in like that, so this is when I started using the algorithm. So these are like PTC lines, and to get to like its superconducting state, the telescope is using like cryocoolers, and like to lower the temperature of that, we're using pulse tube cryocoolers by Cryomag. So these are the lines from from that. So if you I'm not sure if you can see like the blue line on like the first graph. So this is a part of the resonators and the detectors. So this would be like between like 1 and 4. Like the frequency range is between like 1 and 4. And as you can see in the detectors, our algorithm picked up noise at that point. That is like the 1.44 hertz line, but it didn't pick up anything in the resonators. So that was pretty interesting. And we continue to run the same algorithm through like different frequencies and increments of 1.44. So like from 1.4, we go to 2.8 and then 3.8, yeah. Yeah. So we essentially got the same result where we only got pickup in the detectors and not the resonators. And then from there, like, I don't know if you can see the little like legend over there. You have the amplitude and the frequency. So it's pretty cool because like it shows you the frequency and the amplitude of the sine wave at that point. So from there, I plotted like a histogram of the amplitude that the algorithm picked up. So as you can see, we didn't get anything in the resonators. We got a like pickup in the superconducting and like the normal detectors. And then, so in order to investigate this, we started off with a few possibilities. We started reading them out, and we suspected that, okay, so what we're picking up is magnetic signals. And in order to investigate that, my mentor, who is in San Diego right now, used a magnetometer and placed it around, this is like the motor, and placed it in like different areas to see what we would get from that. So from that plot over there, we have so yeah, so we have the frequency that the magnetometer picked up from when he placed it on the motor and on the compressor like above the window. And we also plotted like what we got for the 1.4 hertz frequency to compare and contrast. And from that, you can see the like the peaks on, I don't know if that's just too loud, but like the peaks on like the PTC motor and and like the multiples of 1.4 hertz, they perfectly align. So we came to the conclusion that, okay, so these is magnetic pickup from the motor. And then from there, we went on to look at flux ramp lines. And flux ramp, that would be the signal from like a 4 kilohertz signal from the retransmission model. And so we had 6 frequencies to look at in our data. And yeah, so this is a plot of the 3.28 hertz. And for this one, we got pickup in pretty much everything. So that was, I don't know. So we looked at 5 different frequencies, and we created like histogram plots of the flat amplitude. And from there, you can kind of see like they essentially have like the same spread, like the same distribution. And yeah, we used that to compare to and then we went on to investigate this by determining the flux ramp changes and whether that was responsible for the peaks that we were seeing. And the blue part is the original data. So I don't know if you can see the peaks in all of that. Like, I don't know what the thing is, but yeah. So the peaks, and then the orange part would be once we changed the flux ramp frequency just a little bit to see if there would be any shifts, like to determine whether or not what we're picking up is from that. And it turned out to be so. So yeah, I think yeah. So to conclude, I'd like to give thanks to my mentor Jake, who has been great, and the SAT team at UCSD for their consultation. Casey, thank you. And Hakeem and everybody else, thank you so much. That'll be it.
Okay. Yeah, so the slide before the what's it called? I think it's the histogram line, like it's right before that one. Yes, before
This
this
one.
one. Yes. Go one back.
Oh, back
Yeah.
to which
One
histogram?
just one back.
Oh, this one?
Yeah, that one.
Okay.
Yes. My question is, what's the purpose of the horizontal line?
Oh, the purpose of the horizontal line, what? So the vertical line is to find the freed frequency and the horizontal line for the amplitude.
Okay.
So yeah,
Okay.
to pinpoint like what our algorithm is finding as like, okay, yeah. Any other questions?
So, the idea here is to track down any magnetic contamination that's affecting your detectors. Is that right?
Um, it wasn't clear at the very beginning that it was magnetic. So we started off with a more like just generalized approach, like, okay, so this is what we're seeing, what could it be? And then from there, using the other data that other people had collected, like what we would expect the graphs to look like if it were like thermal, or what we would expect to see if it was like radio frequency. So yeah, so and then we narrowed down to magnetic.
And so, do you have an idea what it is that within the system that's causing that magnetic thing?
Oh yeah, the pulse tube motor is the thing that's causing it from the previous slide. So yeah, we use like a magnetometer to yeah.
And so then what do you do next now that you know that that's the case?
Yeah, so from here, I think we're going to consult like the noise characterization team of the Simons Observatory to see about like possible shielding techniques that we could incorporate. And then I think we also have like a few more tests to do. We also have like a few more like a lot more data to look at. So yeah, from there, yeah, we'll look at possible shielding that we could do. Yeah.
I just like to add a comment as a hardware person myself. When you do projects like
Could you use your seat mic, please?
I just want to give a shout out to hardware. But as you're learning skills and detectors and things like this, these are like incredibly valuable skills, right? And so if you get the opportunity to actually touch things, and did you get that opportunity at all?
No, but I'm going back to California this Saturday, so I'll get to see it in person. I'm really excited.
Yeah, so if you can get some actual lab hands-on stuff, that will be excellent to go along with this knowledge you've gained.
Yeah.